message here, and today we're gonna lay the foundation for a new chapter, and we're gonna understand the chapter logically, okay? And what have we done till now? We have understood what a relation is. We have also understood what a function is, isn't it? And we have understood what is a bijective function. Yes, and why exactly is it important for us to define if a function is a bijective function? It's only because we need to identify if the function has an inverse, or is the function invertible. So in the last videos on functions, we have understood how to prove a function is bijective, and how to find out the inverse of a function. And we also realized that bijective would mean 1, 1 and on 2. Basically, when I'm looking at a bijective function, it will look something like this: connections or associations, or relation from this set A to this set. A correspondence from this set to this set is going to be like this, so that when I'm looking at this function from this end to this end, it's going to be a function, and from this end to this end is also going to be a function. Okay, and that's exactly why this is invertible. Say for example, if I had something like this, which is not a 1, 1 and on 2 function, it's a function from this side, but it's not a function from this side, so this function is not invertible. Okay, that's the basic idea that we learned, correct? Now what we're going to do is we're going to learn sine functions. Let's look at a sine graph. That's my cos graph. Let us look at a sine graph. That's my sine graph, right? Now, what I'm going to do is to draw a straight line here. Like this. Consider that to be a straight line, please. Now when I'm drawing a straight line here, I do see that the line is actually cutting the graph at multiple points, which is here, 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 and here, correct? Now let's understand this. For sine 0, the value is 0, so the point is here. So sine pi by 2 is 1, and exactly why? The graph goes up like this and then comes down for sine pi, and again 3 pi by 2, it's a -1, and now it goes to 2 pi, it's a 0. And this is a periodic function, which means this section is going to keep repeating itself over and over again, even at the left hand side and even at the right hand side. That is a periodic function. It goes in a cycle for me. So I now know that for multiple values of x, there is one value of y. Basically, I have multiple values of x like this. Multiple values of x here. And there is one single value of y, and all of them getting connected to this particular value. And I already know that this is not an inverse function, because when I'm looking at this function from this end to this end, it's not going to be invertible because it's not a function at all. And exactly why there is no inverse for a sine function. I cannot define an inverse, right? So what I'm going to do is to, instead of considering the entire domain here, I'm going to restrict myself from this point here to this point here. From this point to this particular point, the function has unique values of y, and for these values of x, the values of y is also going to be unique. And exactly why I'm going to restrict myself to this particular values of x. You getting me? So for sine inverse of x, that's a sine function. So for sine inverse, okay, so x is going to be equal to sine inverse of y. What's going to be my domain? It's going to be all the values of y from this to this, which is going to be -1 to 1, correct? And my range, which is restricted, is from -pi by 2 to pi by 2. Okay, so that's the basic idea behind inverse trigonometric functions. So what I'm going to do basically is to restrict my range, which is going to be from minus pi by 2 to minus pi by 2. And again from this particular section, which is pi by 2 to 3 pi by 2, again the function is going to be invertible in this period. You getting me? So in chunks the function is invertible, but overall it is not invertible. You cannot find the inverse of sine overall, but in chunks certainly you can. Okay, now let's move on. Let's look at the cos function. That's a cos function for you. It has the same behavior as a sine function, which means it's a periodic function. It keeps repeating its values over the period of time, and also it is not invertible. So if I draw a straight line here for a value of y, there are multiple values of x. Look at that. These are the values of x. There, that's x, x, x here, x here, and x here. All these values are getting connected to one particular value y. This might be a 0.5. It's the same 0.5 here all over, isn't it? And that's exactly why I already know that this is not a 1-1 function, because when I look at this from the other side, or when I look at this as x being connected to 1, 2, 3, 4, when I look at this, look at these points, they all get connected to a single value y, whatever that value is. So when I look at this function from the second set in this fashion, it is not invertible. I cannot find the inverse of it because the function is not 1, 1 and onto, because the function is not a function at all when I look at it from the other side. And so what I'm going to do is I'm going to restrict this to what? To 0 to pi. Okay, so when I restrict it from 0 to pi, I see that for every value of x there is a unique value of y. Okay, whereas if I had restricted it from pi by 2, let's say for pi by 2 to pi by 2, like how we had the sine function, which is being restricted from pi by 2 to pi by 2, there you go. If I do that here, for two different values of x, I have the same value of y. And exactly why? I'm not going to pick this up. Instead, I'm going to pick this to this. So what am I doing here? For cos inverse of x, y is equal to cos inverse of x. My range is going to be what? 0 to pi. And my domain is minus 1 to 1. Okay. Now what about the tan function? For the tan function, you can see that it's not been defined for a multiple of pi by 2. Any multiple of pi by 2, be it negative or positive, it's not been defined. It goes to infinity, correct? And again, if I draw a straight line, it's going to cut the curve at multiple points. So for different values of x, I have the same value of y, and y, that's exactly why this is not an invertible function. But again, in the same fashion, what I'm going to do is to restrict my range, which is the y value. So I'm going to restrict it from minus pi by 2 to pi by 2, with pi by 2 and minus pi by 2 not included because it goes to infinity, which has not been defined. So I'm going to put a small bracket around it. And what's my domain? This is my range. And what's my domain? My domain is going to be all the real numbers, because look at this y value, it's taking all of them till infinity. So all the real numbers. Okay, so that's my secant and secant function. Okay, and here too the function is not invertible. You can see that already, isn't it? So for this value, if I can draw a straight line here, which is going to be called as the horizontal test for checking if the function is invertible, because when I draw a straight line, I have multiple values of the curve being cut by the straight line, or multiple points being cut by the straight line, and this tells me that the function is not invertible. So the value of x, value of x, value of x. So again, what I'm going to do is to restrict myself to a particular value. Let's see, what am I going to do? I cannot take this, which is minus pi by 2 to pi by 2, because you see there's already two values of x connecting to one value of y, and so I'm going to connect or take this from here to here, from here till here. So what happens, the value of y is here, goes till infinity, and then it starts from here and goes to infinity. And what is this value? This is a 1 and this is a -1. Any values between 1 and -1? Nothing. And it goes till infinity. Correct? But it's not been defined at pi by 2. So keeping these things in my mind, I'm now going to write my domain and the range. So for x being equal to secant inverse of y, my domain, which is the values of y, is going to be anything except for values from 1 to -1, isn't it? See, after -1 is going till infinity, after +1 is going till infinity, but nothing between -1 and +1. Correct? So that's going to be my domain. R, real numbers are minus -1 to 1. Some textbooks would write this and some textbooks would write this. Modulus of x is greater than or equal to 1. Modulus of y. In this case, it's going to be a y. In this case, it's going to be a y. So I'll have to write a y here. And my range is from 0 to pi except for pi by 2, because pi by 2 has not been defined. So 0 is included, pi is included, except for pi by 2. Getting me? So you can also understand this as it is a reciprocal of cos, isn't it? So look at this. Cos also has the same range, except that the pi by 2 is not been defined for us. Getting me? Some textbooks will write this: 0 to pi by 2, 0 included, pi by 2 not included, union, there is no negative here, and there is no negative here, and again pi by 2 to pi, with pi being included. You get it? Okay, so that's going to be my domain and the range. Now let's look at cosecant function. I'll come back to that table. Let's look at cosecant function. Again, this is not a invertible function from here to here. I can see that there's going to be multiple values. Again, I'm going to have a curve, something like this, and a u here, and a parabola basically. Okay, not here. Okay, yeah, that's there. So it is not an invertible function, but I'm going to pick up the intervals for it. I need all the values of y, which I can get from here, from this particular point to this particular point. However, for this point, the value of y has not been defined. So that is all it is. So what's my range and domain? Let's see. So for x being equal to cosecant inverse of y, my domain, which is the y values, is going to be all the real numbers, isn't it? Except for this part where the function has not been defined. And what is this? This is from -1 to 1. Look at that. -1 to 1. There's no values. The graph is not going to come in between these parallel lines except for -1 and 1. And again, here you can write modulus of y is greater than or equal to 1. Some textbooks go by this, some textbooks will go by this. But the meaning of it is the same. What's going to be my range? My range is the one which I have restricted, minus pi by 2 to pi by 2. This is a pi by 2 to pi by 2, except for 0, because it's not being defined at that particular point. Some textbook would probably write this as to 0 union 0 not being included to pi by 2. It means the same. Do not get confused. Different textbook would say different things, but ultimately the concept or the meaning behind it, it's the same. So if I'm looking at this on a table, That is what I see. Getting me? So this is in our case, there's going to be a x here. There's going to be a x here, x, 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 and a x. Okay, so sine inverse of x is going to be, this now becomes my domain, and this is my range. Okay, so what happens? It's the same thing, whatever I've explained. Okay, please go ahead and refer to the cot function. I've left it out for a reason. I want you to understand that, okay, by yourself. Wonderful, wonderful. So these are called as the principal values, okay, or the principal branch. Why is it the principal branch? I've already explained to you that the function is invertible in chunks. It's not invertible all over, but it's invertible in chunks. But this branch, from where I'm going to be picking up values, this branch will be called as the principal branch. So whenever somebody asks you for the principal value of a certain function, you will have to look for sine values or the y values of sine inverse in this particular branch. Okay, perfect. With that understanding, I would like to stop this particular video. It's been a very informative video, okay, and this explanation will be laying a foundation for the next coming questions in the exercise 2.1 and so on. All right, very important concept. Without this understanding, it's very difficult to proceed with inverse trigonometry. You see, all these chapters are connected. Relations is connected to functions. Function is connected to trigonometric functions, inverse trigonometric functions. And if you go back to relations is connected to sets and relations, and then we have the inverse function, and then we have the inverse trigonometric function. And you'll also discover that sets is connected to probability and also to permutation combination. Okay, so there's no chapter that you can learn individually. Probably in your other subjects, I'm not sure. I think in chemistry and biology, you can segregate the chapters, and if you learn a chapter, you don't need to kind of be associated to the other chapter. In this, all the chapters are connected, so you cannot say that I've finished a chapter and I'm going for a next chapter. You would ideally need to think about it as a concept. You finish a concept and go to the next concept. You cannot say chapters. Okay, so with this, we're going to stop this video. Thank you for watching the video, and please subscribe to it and advise your friends to watch these videos and learn something from it. And if you think that there was something that I missed out or something you need an explanation for, please write the same thing on the comment section. Share the videos and subscribe for it. Thank you.